less than 30, what we're going to do is first ask ourselves if the population is normal. If the population is normal, then the sampling distribution is still going to be normal regardless of that sample size. Again, I think it's really important to note here that we're going to use T procedures if sigma is still unknown. So very big bullet point there. So go ahead and make a little star in your notes that that's going to be a giant bullet point that we need to make sure that we know. That if sigma is unknown, that you must use T procedures. Let's suppose here that the graph, the population distribution is not normal. If the graph, excuse me, I keep saying graph, should be population, I'm saying. If the population is not normal, then we must graph our data, especially if the sample size is below 30. Because remember that this is the category that it's below 30. So remember, if our sample size is large, we can use the central limit theorem to assume the sampling distribution is approximately normal. If it is not large, it's okay if it's not large and the population is normal. We know the sampling distribution will also be normal. However, if it's not normal, we got to actually graph this. So what we're going to do is we're going to create a box plot, a histogram, or a dot plot. Okay, and we're going to look at the shape of these graphs. If the shape of these graphs is approximately symmetric, we're going to go ahead and infer that the sampling distribution of that sample mean is going to be approximately normal as well. A big note here, and again, I would really highlight this. If they give you a graph, don't remake a graph. One year they gave a stem plot, and you could have used that stem plot and just looked at the shape of the stem plot and commented on that shape. A lot of people redrew a graph. I'm like, why would you redraw a graph? It's already right there for you. So just be aware or cognizant of the fact that if they give you a graph, just comment on that one. And what we're going to do is we're going to make this statement here that if the shape is approximately normal / slight skew with no outliers, we're going to go ahead and use T procedures there. The big deal here is if you do have an outlier, then you should not continue. If you have an outlier, if there's a clear outlier, that means that that distribution will not be approximately normal. Approximately normal distributions do not have outliers. They don't contain outliers. So it's kind of silly for us to assume that it is normal with an outlier. A rule of thumb here is that if it's not normal and there is no graph, you can proceed with caution, quote unquote, just with the kind of like idea in the back of your head that if you continue, your results might not be reliable. All right. So your results might not be reliable. So I really would suggest maybe if there's a possibility of increasing sample size that you do that, but we can go ahead and do the test or interval anyways. And then kind of just say with a disclaimer, well, our results might not be very credible due to the low sample size and the shape of the graph. Yep.
I was going to ask you to include this.
I would, yeah, I would include that disclaimer. I think it's very rare that you're going to see this case, but if you do happen to see it, then yeah. I would say that generally you're going to get a sample size that's at least 20 normally, at least 20, or if it's lower than that, the population distribution will be normal. So you're able to kind of continue on. All right, but we're going to look at an example now that kind of highlights when we do this. So you guys are going to need your calculator for this example. So Consumer Reports tested 14 randomly selected brands of vanilla yogurt and found the following number as calories per serving. So those are listed there kind of in that chart table thing, right? We're going to compute a 98% confidence interval for the average calorie content per serving of vanilla yogurt. Okay, so what we're going to do here is this time, do you see how they gave us all the data points? But there's only 14 of them, correct? So something in the back of your mind is, if I'm going to construct a confidence interval, and I only have 14 data points, I can't really assume that the population is normal because it's not stated, correct? I also can't use the central limit theorem idea that my sample size is quote-unquote large enough to assume normality. So what we're going to do with these data points is we're going to need to construct one of those graphs, a box plot, a dot plot, or a stem plot, and look at those data on a graph. Does that make sense? Okay. So the additional step today is if you have a sample size that's lower than 30, you're going to have to actually look at the graph of the data. If there's not a graph, graph it. If there is a graph, comment on it and see if it's approximately normal. Okay, or approximately symmetric, so you can assume it's approximately. Does that make sense?
Yeah.
All right, let's go ahead and start the same way we normally would start. You guys ready? How do we normally start a panic? State your parameter. What parameter are we talking about? Are we talking about a proportion or are we talking about a mean? What are we attempting to estimate here, friends? The average. Average implies mean. So we want to estimate, what is the parameter for a mean? Mu. Thank you. You're going to estimate mu, the true average calorie content per serving of vanilla yogurt with 98% confidence. Oh, do you want a copy of them? I prefer that you don't leave them at home. Well, I wrote on this one. The only one I have is kind of written on. All right, Trevi, we're just going to get the written copy. Don't spoil everything for everybody. All right, so after our parameter assumption, what do we do? Or parameter state. I kind of already gave it away. You're going to do your assumptions, right? What's the big assumption here that we're going to need to check first?
Random sample.
Did it come from a random sample? I'm asking. Yes. So we need to state that it was a random sample of 14 brands. You have a random sample of 14 brands. Probably not a lot more than 14 brands of different yogurt at the grocery store. Yeah. So here, that's why the sample size is a little slow, right? Because, I mean, I don't think there's like 50 brands that you can go and try. I mean, I guess you could, but that might be a little tedious, right? Okay. So that's check, right? However, do you guys notice that our normality check, when we're kind of checking for normality here, 14 is less than or equal to what? 30. So now it's time to actually use those data points and construct a graph. Does that make sense? Okay, so guess what we're going to need to do now? We're going to need to pause our panic, and we're going to need to go to our calculators, and we're going to need to type in the data that we were given. Are you guys with me on what we need to do? So we're pausing, and we need to actually construct a graph using those data points. And what I want you guys to do is you do need to use your calculator to do this. All right. So the whole idea here is to actually use your calculator to do this. All right. So go to Stat, and then you're going to go to Edit, right? And you're going to need to type this into list 1. All right, Jeremy, list them out for me. Because I gave you my copy, so you must tell me what to put in the calculator.
160,
160,
200,
200,
220,
220,
230,
230,
120,
120,
180,
180.
140,
Oh, hold on. 180. And then you said what?
140,
140,
130,
130,
170,
170,
190,
190,
80,
80.
120,
That's low. 20,
100,
100,
and 170.
and 170. All right. And that time you should have been able to do that, correct? All right. You're going to go to y equals. All right, we need to turn this plot on. Okay, so go to y equals. Make sure your stat plot's on. So we're going to go to second stat plot. So do you know where stat plot is? We talked about it earlier in chapter 1. Second y equals. You guys remember getting there? So I turn that on. All right, and we're going to need to create a graph. Now, you're going to do this with your calculator. Do you guys notice that all this is calculator active here? This is how you should be doing it. I don't want you doing this by hand. That's too much time, right? So what we're going to do here is we're going to have to pick a graph. Now, which one of these do you think is going to be representative of the shape that we need to see? Which one's the best at discerning shape? Because we need to look at the shape of the data. Probably need to look at the histogram, correct? You guys with me about the histogram? Because histogram is going to tell you the shape real fast, right? And then what do we need to do? We have list 1. Is that where we put our data?
Yep.
Yep, cool. So we need a graph. Now that doesn't look like my data, right? You guys remember how we can get the nice graph? You hit the zoom button. Remember what class are you in? Those zoom stats all the way at the bottom, 9. Bam. Got that? Okay, so what I want you to do is I want you to take a look at this data. Would you say that this is an approximately symmetric graph? Really? Which way is it skewed then? It's ugly. Okay, well I didn't ask if it was beautiful. I asked you if this is an approximately symmetric graph.
Yeah.
I mean, I guess it's approximate.
I mean, it doesn't have to be perfect. You guys are all about perfection. Sometimes data is not perfect. Sometimes it's really dirty. You have to go, like, sometimes they do this thing called data mining, and you have to kind of like sift through data for what you want to see, right? Here, not the most beautiful thing in the world, right? Okay, but I'm going to ask you again. Is this clearly skewed in a direction? Can you say that this is roughly symmetric? Yes. So guess what we're going to do? You're going to copy down the graph of this on your calculator below like your little statement for normality. Okay? So what I'm talking about is this. You're going to literally construct a little graph. Okay? You're going to literally construct a little graph and you're going to copy down that graph. You guys see how I did that here? It does not have to be perfect. If you remember reading, it's a very informal graph. Because what are you attempting to tell me with this graph? That the shape is going to be symmetric. Therefore, we're going to be able to assume that our sampling distribution of the sample mean is approximately normal. I would label this. So what I have here on the PowerPoint here is basically the gist of what you need to have. All right? Do you guys understand what I'm talking about?
You don't really like any numbers or...
I do not want any numbers. I just want the rough shape of it. Just the rough shape. The RUFF shape of this graph. I spelled rough wrong? Oh, I thought it was RUFF.
I mean, that's a dog.
Oh, it's a doll. Oh,
Someone would think it
You're
was.
literally...
I'm going back to school. Okay. Now, we got to make a statement about what we see. We can't just draw the graph and be like, up, done. So we need to make like some sort of little statement here, right? Okay. So make a little statement here. Since the graph to the left, and right today, to the left, is approximately symmetric. That's awkward. Random phone calls from random robocallers with no outliers. We can assume normality. Okay, so we're checking to see if it's normal. So pretty much normal. And then our statement here, because were we given what the population standard deviation is? Answer is no, we were not given that. So what are we using to estimate? S sub x. And what does that invoke that we do? T procedures. Does that make sense? Okay. Very important you know when you use T, when sigma is unknown. What if sigma is known? You use Z. So you do a one sample Z interval. But I will tell you that 99% of the time you don't know sigma. Sigma is almost always unknown. Kind of like mu is unknown in a lot of cases. So we're estimating. We're using statistics to estimate those parameters, right? So we're going to go ahead and name our one sample T interval, correct? All right, so name it and then write down the formula as normal. Okay, so write it and then write down or name it and then write down the formula x bar plus or minus T star times S of x divided by the square root of n. Because we're going to use our calculator to get a lot of this data. Because notice from your stem of the question, you were not given the sample mean. You were not given the sample standard deviation. You were given the sample size. You were not given T star. So you're going to have to go find a lot of things now. But guess what you already done to help you? You put it in the calculator. So now we're going to use the calculator to kind of help guide our work. We're going to have to show our work as we go, but the calculator is going to do a lot of it for you. Okay? So I'm going to go back to my calculator, and this is where you should be on your calculator, correct? Okay, yesterday we talked about what button in the calculator to press, correct? You guys remember?
Yeah.
What? Stat. Stat. We're going to go over the calc. Did anyone check themselves in their calculator today by doing the 1 proportion z interval in the calculator? Why not? Mr. Bird showed you how to do that. It's okay. So you're going to go to the t interval, right? You guys remember t interval from yesterday?
Yeah.
Press enter. Okay, so t interval. Do we have statistics that we typed in?
Yeah.
No, we don't have any statistics we typed in. We don't have x bar. We don't have s of x. I need you to listen to the questions, people. Come on. Do we have any of those? No, but guess what we do have? We do have data. We typed all that data into L1. You see that? What do I need to change this confidence level to? 98. So I'm going to come down here to 0.98, go down to calculate, and boom. Got a lot of stuff. Guess what this is? This is the interval. You should probably write that down somewhere, but leave some space for your work, because you're going to show your work. So leave a gap between, on your notes, literally leave a gap between the formula you wrote and then you plugging stuff into the formula. Go ahead and write down the interval, because what do you know your interval is? 126.16 to 189.56. You've already computed it. Don't waste your time. Use your calculator as a resource. All right, so what's x bar? 157.85. Go ahead and write that in your little formula, because isn't that the first thing? It's x bar. So literally what I'm asking you to do is x bar plus or minus t star times s of x over the square root of n. I want you to write 157.86 there. Plus or minus. Do we know t star yet? No, leave it alone. What else do you know? Yeah, that's the 44.75. Divided by the square root of what? 14. Now, you don't have to compute any of this by hand, because guess what your calculator did? It already did it for you. You should already have written down the 126.16 to 189.56. You're just filling in the pieces of work. You guys see what I'm talking about? Okay. So how are we going to go find this t star?
For inverse t.
Inverse t. Okay, so what kind of confidence interval am I doing? 98. You guys remember what area this is? 0.99. Okay, hopefully you remember. We've been talking about that for the last week. Degrees of freedom. Everyone knows that one. What's my t star? 3.65. Now over here to the side, we probably need to write our degrees of freedom somewhere. We did 14 minus 1, which was what? 13. Okay, see all that? Now I'm going to go back to the PowerPoint, because I already have all this there. Isn't that the same stuff that we had? Okay. So do me a favor. The reason I'm showing you how to do this in the calculator is I want you to use this as a tool. All right? Use it to check your intervals. I'm disappointed to hear that you didn't use that on the quiz. I mean, why not? Yeah, you do. You just hit the, look, let me see how fast it's going to go. Stat, button, test. Go find where it literally says 1 proportion z interval. Down, 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 down. Oh, look. Oh, there it is. Enter. Oh, I have to enter 3 things. Oh, goodness gracious. All right. Here we go. Put in 9 something something over, what, 2350? Confidence level, oh, 0.99. There it is. Check yourself. You do guys realize I'm uploading these to YouTube daily?
Yeah.
So if you're like, how do I use the calculator again? What are you going to go do? Go watch it again. You didn't get it the first time, go watch it again. Speed me up, slow me down, whatever you want to do. Use your resources. Conclude. We are that what? That the interval from? To? Does what? Mean? True mean calorie content, caloric content per serving of vanilla yogurt. I think I rounded to the nearest calorie because generally you don't see 0.16 calories on the back of a yogurt, right? They usually give you like a whole number, an integer, a natural number. Because remember, before this, we didn't know what the true mean was. We're estimating. You're basically saying with confidence, we're 98% confident it's between 126 and 190. Could be in the interval, could be outside. We don't know, but we're pretty sure, we're 98% confident that it falls in that interval. You guys with me there? That's what we're doing. We didn't know it before, but we're saying it's between this and this. How sure are we? Well, 98%. There's a 2% chance that it probably isn't in there, but we don't know if it is or isn't. We can't say that it is or isn't for certain. All right, you guys good? All right, moving on. Follow up. A diet guide claims that you will get 120 calories from a serving of vanilla yogurt. What does this evidence indicate? A diet guide claims that you will get 120 calories from a serving of vanilla yogurt. What does the evidence that we just used, that we just made, say about this? That's false. Why? Because 120 is outside and is lower than what our interval states. So 120 calories is not contained within our 98% interval, or 98% confidence interval, rather. The evidence suggests that the average calories per serving does not equal 120. I think we have some evidence to say it might be a little higher, right? Because at the lowest point, it's at 126. But we know it is definitely not 120. It doesn't have a possibility of being 120. It has a possibility of probably being higher. All right, do you guys have questions? Sure? About anything so far?
Hey,
Miss Cannell.
how are you?
Nice to see you.
You too. So to get the graph, it's stat and then it's just
Type it in the list. And then we do second white.
thank you.
On the graph, earlier, we were talking about outliers.
Yep.
So we just
Do we just like,
ignore them, or like when they're there, what do you do?
well, we can't use key procedures. Like, we can't continue if they're outliers. That's what I'm saying.
So
Then they're there, they're bad. Say hi to the YouTube. We're
Hi.
recording. All right, let's go ahead and do number 8. Let's see number 8?
Yeah.
Last problem of the day. Last problem of chapter 8. Does it say 7?
Yeah.
Here we go. Look.
you can see
Done.
Ew.
Fixed.
I love it.
Thanks. Okay. See you, Canal. Bye. In 1998, this is all before you were born, as an advertising campaign, the Bisco Company announced their 1,000 chip challenge, claiming that every 18-ounce bag of their Chips Ahoy cookies contained at least 1,000 chocolate chips. Dedicated AP statistics students back in the day purchased some of the randomly selected bags of cookies and counted the chocolate chips that were in the bag. Some of their data are given below. So you can see the data here. Construct and interpret a 99% confidence interval for the average number of chips in the bags of the Chips Ahoy cookies.
Wow, let's do it.
Well,
So how many bags do they buy? It looks like.
Uh,
Looks like 16 randomly selected bags, correct?
Yep.
And what do we know about 16? That is a number that is smaller than 30. Do we know that the population of chips is approximately normally distributed? No. We cannot use central limit theorem because of our low sample size. So we must do what with this data? We're going to be graphing it again, right? Okay, so let's start our panic. How do we start? Parameter. Are we talking about a proportion or a mean? Mean. So we want to estimate mu. That is the parameter, where mu is equal to the true mean, true average number of chips in a bag of Chips Ahoy cookies with 99% confidence, correct? That's how we should start. So you always start your confidence interval by stating the parameter. What parameter are you estimating? You're either going to be a proportion or you're going to have a mean. Later in the course, we're going to actually talk about regression lines, and you'll talk about slopes. You're going to be estimating true slopes of regression lines. That's not hard, I promise. That's easy stuff. This is only difficult because it's new. All right, let's talk about the assumptions. What assumptions do we need to have? Random sample. Do we have that? Because they did what? They told you they have a random sample of 16 bags, because you guys told me 16 bags, right? All right, after a random sample, what do we check for? Normality. And the first thing that we should see here is that 16 is less than or equal to what? 30. So guess what we got to do? Graph our data. So I'm going back to my calculator. I'm going to erase all this from the previous problem. And Jervy, you ready, bud?
I was just gonna give you paper.
No, I like you reading it out to me. Stat, edit. I'm going to clear my list. All right, let's go.
19, 1214, 1087, 1200, 1419, 1121, 1325, 1345, 1244, 1258, 1356, 1132, 1191, 1270, 1295, and 1135.
All right. Where do I go to assess the shape? I have it all in there. Graph it. So how am I going to graph it? You've got to make sure your stat plot's on, right? All right, this time I want to show you that if you speculate that your data may have outliers, guess what you could always check here? You check your box plot with outliers. Remember, this graph will automatically display the outliers, correct? So if you speculate it, let's just double check here. So I'm going to change that to box plot with outliers. We're going to do zoom 9. Do I see any outliers there?
No.
No, so that means my graph contains no outliers. Can you assess the shape of this real fast? I know we don't do it often for box plots, but
Yeah.
would you say this is approximately symmetric?
Roughly.
Are you guys okay with this?
Yeah.
We can always go back and check the histogram if you're unsure. So if you're unsure, remember, you can go back real quick, change this to histogram, hit graph, and then this is what you see.
So, but if you were outliers, what would you consider that?
So you don't do it. You just stop. You cannot do it. Yeah, you're done. All right? So this one kind of looks a little bad, right? But
That's how mine is.
yeah, I mean, I just hit zoom 9 after that. But if you hit zoom 9 for the previous, zoom, okay, don't get me confused. It's zoom. You hit the zoom button, and then number 9 says stat. This is not, yeah, number 9, stat. Yeah, okay, zoom 9. That's what I'm doing. Okay. Okay. So right here, we go to, you can hit the box plot with outliers. Zoom 9 gives you this. So, are you guys okay with the shape of this graph?
Yeah.
Okay, so let's go back. Let's just go ahead and draw the box plot, right? So you can draw a box plot, you can draw a histogram. I'm not limiting to what graph you choose. I do want you to graph it though when your data is less than 30, or your sample size is less than 30. And I want you to assess the shape of this distribution. So the number of chips in the bag of the Chips Ahoy cookies, right, are what you should label the graph there. And then we should comment on it, right? The graph shows and approximately symmetric shape with no outliers. Therefore, we can assume normality. I know it's a little irritating when you get the ones that have low sample size, correct? Because you really have to check your data. Yes, Karen?
So this covered yours too, right?
Yes,
So why is this T?
it is. Does it have an outlier?
No.
Use T procedures. Okay. All right. So sigma here is unknown. Again, they did not give you that within the data of the problem. So sigma is unknown. So guess what we're using to estimate? S of x, the sample standard deviation to estimate. All right. So this means that we're going to use these T procedures, right? So next thing for n, one sample T interval. All right. That's the procedure we're going to use. All right. Once you do that, go ahead and write down your formula. X bar plus or minus T star times standard deviation over the square root of n, right? That's our formula. All right, I'm going to flip this back to my calculator because remember, I don't have any of that data, right? I don't have what X bar is. I don't have S sub X. I don't have T star. The only thing I do have is n, which is what? 16. So, but guess what I can do? I can come up here, use my calculator, and I can do this. So remember, what do I hit? Stat, go over to tests. You only know two right now. Two procedures, right? One prop Z interval, that's letter A. Which one is for the one sample T interval? 8. Okay? All right. I don't have statistics because I was given the raw data, correct?
Yeah.
So I'm going to use the data menu. If you're given the statistics, what are you going to do? You're going to go over to stats and you're going to type in X bar S of X n. We weren't given that. So we have to use the data that we were given, and we put it in list 1 already. What was our confidence level? 99. So calculate, done. Okay, so here's your interval, folks. And here's your sample statistics that you need to kind of plug in the formula. Because what have you already written on your paper? You have written the formula, correct?
Yes.
You must write the formula. I'm now going to use this information and plug stuff into said formula. Let's round this to like 0.2. Let's leave a space there for T star times by S of X over square root n. What's S of X? Not 34. Oh, you said 94?
Yep.
Sound like you said 30. My hearing's going, I guess. You guys literally see how I'm plugging everything in?
Yep.
All right. Interval, I'm going to go and write that. 1168.7, 1307.6. Guys happy there? It's the only thing I got to go find now. P star. So I'm going to take a moment, go to second vars. We're going to go down to inverse T. Remember, what kind of interval are we doing? What's our confidence level? 99. What area are we going to use? 0.995. What's our degrees of freedom? If you have sample size 16, how many degrees of freedom do you have? 15. Paste. 2.947. Come over here and put degrees of freedom somewhere, like 15. Just put that somewhere on the paper. And I'm going to convert this back over to the PowerPoint because guess what's on the PowerPoint? All of that. All right, I just worked it out with you. So how are we going to finish this one off? Conclusion. Remember, what are we estimating? The true mean number of chocolate chips, right? Do we know what that number is? No, but we're estimating with 99% confidence. So we are 99% confident that the interval from 1168.7 to 1307.6 captures the true average or true mean number of chocolate chips in a bag of Chips Ahoy cookies, or in bags of Chips Ahoy
Where
cookies.
do you get like the confidence level? Like, obviously,
They give it to you.
yeah, but like, and like, would we use this in the real world?
Yeah.
Like, how would you get this confidence level?
You choose it.
How you just,
The more confident you are, the higher you raise your confidence level.
so it's a estimate.
Mm-hmm. You can't choose 100% confidence because you can't be 100% confident in anything. But you can choose like a 99.8% confidence level. It just means that your interval is wider than other confidence levels. Remember, the two things that control how wide your interval is are the confidence level and your sample size. Higher sample size reduces the margin of error, which lowers the interval. All right. Your confidence level increases the size of the interval the more confident you are. Remember, we talked about confident people, big-headed people. The more confident they are, the harder it is to fit their head in the room, right? Because their interval, their head interval is so big. You can't do that, right? The less confident is shorter, smaller interval. Okay? So you need to know how the confidence level plays a part. So if you want the smallest interval, high sample size, low confidence will give you the smallest interval. But you don't want to estimate with low confidence. You want to kind of balance the two. So that's why sample size is so important here. You want to have high sample size and high confidence to get the best representation. Hope that makes sense. All right, let's answer the final question. What does this evidence say about Nabisco's claim? What was the claim? Is it true? The 99% confidence interval is completely above it. So guess what we assume to be true? Nabisco's claim seems to be true. There are at least 1,000 chocolate chips in each bag of Chips Ahoy cookies. All right, ladies and gentlemen, you have 3 problems to do over the weekend for review. One is a confidence interval for means, one is for proportions, and one is a problem from last year's AP exam. I want to see how you guys fare on it. All right, and we will discuss these on Monday. All right, so there's 3 problems for a moment.
I do remember you were talking about this, but what were you saying you were doing this early?
The practice test, if you want. How many of you guys want your Chapter 7, Chapter 8 practice test already? Okay. All right. Any questions about this before I turn this off? You want to say hi, YouTube?
Bye. Unsubscribe. Unsubscribe.
That's rude. That's rude. Stop.
That's why.
Yeah, don't.
You can edit it.
Yeah, that's what you do right now.
That's really sad.
So,